And so this is table 4-3. So the first thing, when you get a problem like this, the first thing you do is calculate what is my choke pressure under these conditions. So the only thing you need is the heat capacity ratio from this table. If you don't have that, you could do the mono triatomic gas, if that's what you have, right? And the P naught. If we look at this table, you'll see that the smallest one is about 1.11, and the largest one I think is 1.67. So if we look at, if we just do the calculations for these two, the sort of the ends of this, it doesn't mean that this is the only, right? You might have a heat capacity ratio slightly outside of this, but it's not going to be too different from it. But we're going from basically 0.4958. In other words, if you look at a pressure and it's P naught is more than 2 times your atmospheric pressure, or the pressure on the other side, which is normally what we're dealing with, is it's leaking out into the atmosphere, right? Then you can be certain, you can be fairly sure that you have choke conditions.
So if it, assume it's just like a mixture of gases that we don't know what it is, we could just assume that it's like 0.5 and make assumption.
So you can, for air, for example, you can go back to this one, and okay, diatomic in air, you're about 1.4. Okay, but you're fairly safe, I would say, if your P naught is significantly larger than 2 times that, you're going to be under choke conditions. Okay, so let's see how we use this. So our time weighted average for hydrogen sulfide is 10 ppm, and it's stored in a tank at 100 psi gauge at 80 degrees Fahrenheit. We're asked to estimate the diameter of the hole that will lead to a local hydrogen sulfide concentration equal to the TOV time weighted average. If the local ventilation is 2,000 cubic feet per minute, and it's deemed average. Okay, so that sounds familiar, right? You know ventilation calculations. I don't think there was anyone that missed that on the exam. Now there were a few who couldn't convert cubic feet per minute to the correct units, but okay, that should not be an issue. Okay, so TLV time weighted average is 10 ppm. Okay, so what do we need? What do we ask for? So we have a tank of H2S, and if we look at table 4-3, whoops, we can see that the heat capacity ratio for hydrogen sulfide is 1.30. Okay, we have our P naught was the 100 psi gauge, and I'm not even sure that I should write it like this, but I assume it's fine if I put the gauge on there, right? But that means it's 114.7 psi. Put an absolute on that because that's the number we need, okay, to calculate what our peak choke pressure is. It is equal to 114.7 times 2 gamma plus 1. Gamma minus 1. Actually, let me just put not here. And our choke pressure 7. We have 2/2.3 over 1.3, 0.3, and that is equal to 62.595 PSI. Okay, so what was that again? Now, do we have choke pressure or not? Which way was it?
It's true.
It is choked. Okay, because what it, the way to look at it is we have 114.7 PSI in here. When it leaks out of the hole, it's gonna decrease, and it's gonna wanna decrease to 14.7. But our choke pressure is 62, so right here when it comes out, it's gonna be 62.6. Okay, which means we do have choke flow.
Is that like why, let's say like an explosion would occur? So like when you have a hole, it's going out but it's choked, so there's also so much pressure that the tank has to like withhold.
So that's a very good, that's a very good observation, right? So if your tank pressure is increasing here and your relief valve isn't sized properly, you can reach choke flow in the relief valve, so it can only release at a certain rate, and you can get an explosion from that, because the rate of pressure increase here is faster than it can be released, and then all of a sudden you have reached the limit of the vessel. So that's certainly one way. That's probably what happened in T2. Right. Now that pressure increase, of course, was due to reaction, but at that point it doesn't really matter where it comes from. But the relief valve wasn't releasing fast enough. Okay, so now what were we supposed to do? Okay, so we need a hole that will give us a concentration that's equal to the time-weighted average. Okay, so it's obviously, we have to use this equation. Don't forget that 10 to the 6 over there. Just the same. Because what happened on the exam is that you went from definitely overexposed, if you have the 10 to the 6, to not overexposed. In other words, you just killed someone, right? If you forgot that factor of 1,000,000, right? So the lesson from the exam, right, or really from all of this, if you have a spill of a highly volatile compound, you know, almost anything, the time rated average, this was 10 ppm, 100, you are going to exceed the time weighted average. It's not, you cannot have a pool of liquid evaporating into air and be below the time weighted average. There's not really a ventilation rate that can reduce that below what you need it to be. That's the bottom line. So this is what we're dealing with when we have leak through a hole or anything leaks, is really emergency response things. It's not for, you know, by that time, workers are gonna have been overexposed, right? So you have to limit their exposure if they're working with it day in and day out. Okay, so we knew that this was 10 ppm. Okay, but we were asked for the area, and since we have, so we need our QM, and in our case, it's QM choke, which is equal to T naught area 0 and GC molecular weight. Let it be 0, and then my 2 gamma plus 1, gamma plus 1, minus 1, and square root of 1. Okay, so here is what we're asked for, right? Actually, we're asked for diameter, right? But you first have to calculate what QM is from this equation. You were given QD, it was 2,000 cubic feet per minute, which, if we do the conversions, it is 5664 cubic meters per minute, right? So one thing when you're doing human conversions is to look at a rate like this. So our 3,000 cubic feet per minute, for example, is about 1.416 something cubic meters per second. Okay, that will help you on an exam if you can remember some of those conversions that are common. Yes.
Is the P in the CPPM formula, that's PATM?
This
Atmosphere.
is atmospheric conditions. Yes, very good observation. We need to keep our pressures separate here. We need to know what they're for. So this, right? It's simpler in this case than liquids, because remember, we were calculating a QM liquid leaking out of a container. That QM has the same symbol, right, as the QM vapor that's leaking out, or the evaporation rate that we calculated. But we couldn't take liquid flow rate in that case, right? We have to look at what leaks out first, what size pool that makes, and then calculate the evaporation rate from there. Now we have a gas leaking, so we can use QM directly. But this calculation is done with at atmospheric pressure, right? This is outside of the container. Okay? While what we're looking at is P naught, that's the one in QM, and then we have another pressure which we're not going to use again. Right? This P choke doesn't really come into the equations that we're using. Right? We just calculated that to see where that is compared to atmospheric. Okay, but this P naught is the tank pressure, and so let's calculate QM first, since we need that to solve for the area. And we have QM RT with 80 degrees Fahrenheit, which if we convert it is 229.67 Kelvin. Okay, and RP in this case is 1 atmosphere, or 0.013. 5 pascals. What else did we have? So what else do we know? We know that CPPM, right, or our time weighted average is 10 ppm. That determines our K. That determines the ventilation coefficient, right? So it's less than 100. Less than 100. And then what did we say? It was deemed average, right? Okay, so that from, gives us that K is 1/8.
Is that right? Is it 229.67? Because that's
More.
26
Oh, wait a
points.
minute. No, it's 3. 300, sorry. Let me see if I, oh. 26. It should be 299, right? I had
Yeah,
299.
That's what I got, it's 299.8.
299.67, thank you. So our QM that we're solving for is CPPM, AQV, over R2, 10 to the 6. 10, 1, 8. What do we have? What do I have? Per minute or per second? I guess I calculated this in minutes. Okay, times 1.03, that is Newton per square meter. We have 3408 grams per mole, which you can get from the table in the back of the book. And 8.13. Oops. That is joules per mole in Kelvin, or Newton meters, and there's your 299.67 Kelvin and 10 to the 6th. Okay, if we do that, we have QM is 0.0981. That's now in grams per minute. And that is equal to 1.635 10 to the minus 6 kilograms per second. Okay, so that's now the QM we calculated for here.
And the area?
And the area is what we're asked for. We're trying to solve, actually we're not solving, we're trying to solve for the diameter. So the question, the problem was, what diameter hole will give us basically a leak rate that will give you a concentration that's equal to the time-weighted average of hydrogen sulfide.
Well, how did you find the QM if you don't have the area yet? Because you have CPPM, you use that top equation.
Okay, so what do we need? We need, what's C naught?
One.
1.
Oh,
So
okay.
C naught is equal to 1 because that's what we needed to do, use on the choke conditions. Okay, and then let's look at, so we have gamma GC, that is our molecular weight over RT0. And that's 1.3 times by 1.0, that's kilogram meter per second squared Newton. We have 3408, 10 to the negative 3 kilograms per mole. 314, that is Newton meters per mole in Kelvin. And we were at 299.67 Kelvin. That is equal to 1.778. 10 to the negative 5. That's a 5. And we're left with kilograms squared, seconds squared, and Newton squared in terms of the units of that. So that's the first one here. This one. And then we have 2 over